We've been introduced now to constant acceleration, and I want to talk about another form of constant acceleration. So this is the acceleration due to gravity. Specifically, we're going to talk about the acceleration due to gravity here on Earth. On different planets, this value would be a different number. So I'm speaking specifically now about an acceleration. It's still A that we typically use for acceleration. But in this special case, we'll now give this a new letter, g. And the value of g is 9.81 meters per second squared. Still meters per second squared because this is an acceleration. So what this means is if you were to be in a helicopter that was hovering above the earth some distance, and you had a parachute and you hopped out, you would start at rest because the helicopter's hovering, it's not moving. So as soon as you step off that helicopter, in that instant, you're not moving, but you immediately start to accelerate downwards. And for every second, you'll be going approximately 10 meters per second faster. You'll keep going faster until you reach something called terminal velocity. So there is a maximum speed that you can fall through the air on Earth. So since this is an acceleration, since this is a constant acceleration, we can use our kinematic equations that we've already learned. So for example, we learned that V final equals V initial plus an acceleration times time. And originally this was a times t, but now we're calling this g times t for this special case. And we had a second kinematic equation. We called it originally delta d or delta x. It's just indicating some change in position. Since we're going to be dealing with vertical motion that's up and down, so we would typically think of that as the vertical axis on an xy axis, I'm going to call this delta y since we'll be moving up and down. And this now is equal to v initial times t. This is the rectangular component of the velocity versus time graph, plus 1/2 gt squared. Originally, this g would have been an a. So we have these two kinematic equations, and we can use them to solve motion problems. So what these equations do is they can describe the motion of an object in free fall. And all that means is any object that's moving through the air is under the effects of gravity, and its motion can typically be described by these two equations. So the simplest case would be if you would throw a ball upwards in one dimension. So the ball would just be traveling straight up and then coming straight back down. And what would that look like? Well, initially the ball leaves your hand, and as soon as you throw it upwards, it's moving as fast as it possibly can in the upward direction. So this initial velocity vector is the longest. So you throw it really hard, and it immediately starts to slow down. Hopefully that makes sense to you. If you go outside and you throw a ball, it's going to start to slow down the higher it gets because gravity is pulling it downwards. It's working against the velocity. So it's going to reach some maximum height and it's going to stop. And then it's going to come back down towards Earth. And I'm drawing these side by side, but they would actually be on top of each other because remember, we're throwing the ball up in a perfectly straight line. And so it would do the opposite now. It would speed up towards the Earth, which is hopefully how you would expect it to speed up. Just like if you would hop out of the airplane or the helicopter with a parachute on. So that's the motion of a ball in one dimension. You throw it upwards, it's moving very fast, and it starts to slow down, and then it gets to its top, its highest point, and it starts to speed up, moving down towards the Earth. So what would that look like on a graph? So this graph here says d for distance, and we're looking at distance versus time. Well, in the first period of time, it moves the most. So its velocity is the highest over the first period of time. So this slope is initially going to be very steep for the first period of time. And as it continues, it's going to be moving slower and slower over time, until eventually it's going to reach a point where it flattens it out. And I'm actually going to draw it from this other side just so I can make the parabola, which is the name of this shape, hopefully as nice as I can. So that's not a perfect shape, but it moves fastest initially. This slope initially is very steep. And then as it continues to move with time, the slope gets less steep. So, here the slope would be about like this, and then the slope is like this, and then the slope is like this. And eventually the slope is going to be perfectly flat here at the top. And that is the position where the ball stops moving at the top of its trajectory. So this would be this point over here where the ball stops moving. And how do we know that? Well, what is the slope right here of the top of this parabola? Well, the slope at this point is 0. So at this point, the velocity v equals 0 because the slope is 0. The rise over the run is 0. And then what happens after that? Well, we're coming downwards now. And now we're on this right side of this little dot diagram. And now the slope's negative, and it gets faster and faster as it approaches the ground. The slope gets steeper on this side. Now, you're looking at this, and one thing we can't be confused about, we have to pay attention here to the labels on these two axes. We have distance versus time. This is not an XY position graph. In other words, this is not the movement in 2 dimensions. What we're looking at is movement in 1 dimension with respect to time. Another type of graph, which we'll learn about later in the class, will have position in 2 dimensions, and then this will be y and this will be x. And at every point along this graph, now we're measuring the xy coordinates of some position of this ball. That's not what we're doing over here. Over on the left, we have time, and this is movement in just 1 dimension, up and down. So that's just one thing to keep in mind as we're looking at this. So far, we're only looking at motion in 1 dimension. This is a ball that's being thrown up and down. So what then does the velocity versus time graph look like? So far, we've looked at position versus time, how it changes over time. As it's being thrown up, it slows down. As it moves towards the earth, it speeds up. So it starts at some maximum positive velocity. Again, we said over here, initially the slope is very steep. So it's positive because the slope, the rise over the run, is a positive number. So we start at some positive value, and the velocity begins to decrease. Again, this graph is velocity versus time. So this is the actual velocity. And where does it hit 0? Well, at the red line over here, the velocity equals 0. And that's what we see here. V versus t equals 0 at this point. And then the velocity becomes negative. Because why? Well, the slope is negative. Now the rise over the run is negative. And so it continues this straight line moving downward. So that is the velocity versus time graph. It's a little bit more simple, but it starts at some positive value, and then it hits 0 at the top of the trajectory, and then it goes negative because it starts moving downwards towards the Earth. Finally, we're going to look at one more graph, and this is perhaps the simplest graph. So what is the acceleration over the period of time that this motion is taking place? What kind of acceleration do we have? Well, we said that we have constant acceleration. So constant acceleration means that the acceleration is the same throughout the entire trajectory of this object. So how do we represent something that is constant on a graph? Well, if it's a constant value, then it's not going to change. So I'm going to write, this is my acceleration versus time. And I'm just going to put, I'm choosing a specific spot here. These aren't to scale. These graphs, these three graphs aren't to scale. We're only interested in the shape, the behavior of these graphs. But I'm going to label this G for our special acceleration. And again, constant acceleration is just going to look like a flat line. So at every point during this object's motion, there's constant acceleration that is acting on the object to pull it downwards towards Earth. The acceleration doesn't change at any point along this object's path, which, bear in mind, this is, again, a straight line up and down motion. We're just representing it over time. At every point, gravity is pulling this ball downwards. And it started with some large positive velocity, v, and then it begins decreasing. So v is changing. V is changing over time. And what causes v to change? Well, we know by the definition of acceleration, acceleration is the change in velocity with respect to time. And we see that not only is velocity decreasing for the entire duration of the ball's trajectory, but at any point on this graph, we see that acceleration remains the same. The slope is the same for every interval when we measure the rise over the run of the velocity versus time graph. It doesn't matter what section we choose, the acceleration will always be the same for this velocity versus time graph. And that's the case because, well, look, our acceleration is constant. We're working with a constant acceleration g that remains the same at any point on the Earth. So that's a lot of information. It's a little complex. We've got three different graphs. V, velocity versus time, is the slope of this previous graph, this position versus time. Acceleration is the slope of the velocity versus time graph. So each one of these is the slope of the previous one. Each one describes how the previous one is changing. Acceleration describes how velocity is changing. Velocity describes how position is changing. So hopefully that makes sense to you. We will be working more problems and we'll be investigating this further.